Listen now to overview the complex numbers from the basic definitions to the geometric transformations. The number I, which square is -1, is of course very important. You see the two axes, the real axis and the imaginary axis. You see that numbers and points are very closely linked. The number is called affix of the point. Each number has its conjugate, and the two numbers are reflexive by the real axes. You see that they have the same real part, x. You see with this animation that the 2 points have the same x, but the number y is opposite. So real part x, imaginary part y. And a new number, so the bar z, is the conjugate. It's the notation for the conjugate. For the operations, you can recall that C, the set of complex numbers, is a field. So all the operations have the good properties. Addition and subtraction are very easy. We add and subtract real and imaginary parts. You see it on this animation, and you see that the addition acts just like the addition of vectors. We add up the real parts and the imaginary parts. Important to notice here that z times bar z equals a sum of two squares. So it's always a sum of squares. And we see next that it is the square of the modulus. The reciprocal of a non-zero number is the conjugate over the square of the modulus. Some exercise now. And now we see the modulus and the argument of a complex number. The modulus is the distance between the number and the origin, O. And the argument is the angle between the referent vector u, yeah, and the vector OM. You can observe that x equals the modulus times the cosine, and y equals the modulus times the sine. It's important that with this we can calculate easily the trigonometric form. And you see that the trigonometric form is the modulus times cosine plus I times the sine. And next, the polar form r times exponential of I times theta, where theta is the argument, and that is explained by the trigonometric formulas, and you can observe that the modulus of a product is the product of the modulus, and the argument of a product is the sum of the arguments. And the same for the division, where we subtract the argument. And you see also the reciprocal of a non-zero number. And we find again the product of z by bar z is the square of the modulus. Important to know how to obtain a polar form. You see that first we calculate the modulus and then we obtain the argument with the trigonometric circle. One example here. Calculate first the modulus, it's very easy, and then we obtain theta, the argument. Some exercise. It's very important to be well trained with this. Now, the vectors, we see that the affix of a vector is the difference between the affix of the endpoint and the affix of the origin. A fair ratio, it's important because it gives two informations. First, a relationship between the magnitudes and, secondly, the angle between the vectors. Two examples. The first, to prove a triangle is equilateral. The modulus are the same, and the angle is pi over 3. The second, to prove a triangle is right angle. And so, you see that the ratio equals r times I, or negative r times I. That gives an argument of pi over 2 or negative pi over 2. The two exercises to find the nature of the triangle. The circle with all the unit complex number. That means that all the numbers around it have a modulus of 1. It's important for you to know very well these numbers. It's very important for the different calculus. And you can check that the modulus of each number is 1. And the transformations now, with the translation, the homothety and rotation. The translation is very simple. You see that this transformation acts like an addition. Z prime equals Z plus the affix of the vector. We add the affix of the vector. And the homothety now acts like a product by a real number. Z prime is the affix of the center plus k times the difference of the two affixes. You see that when you move k, when k is negative, the point M prime goes through the center. And finally, the rotation acts like a product by an unit complex number. See you!